For our second video in 3.4, we're going to be looking at what's called an unbounded region. In this case, again, we'll be graphing our system of inequalities, but they won't close off and make a triangle. It'll actually be open and continue on in one or kind of more directions. It'll be an open space. And again, I'll show you how that works here in just a second. Our example asks us to graph the following system of inequalities, name the coordinates of the vertices of the feasible region, just like our last example. Then again, we need to find the maximum and minimum values of the function f of xy equals 2x plus 3y for this region. So our function is a little bit different from the last function, but again, all we're doing is plugging in our x and y values that we got from our feasible region. Okay, so first off, before we do anything else, I'm just going to change our inequalities into a graphable form. Okay, so we always want that slope-intercept form. It'll make it nice and easy for us to graph. So with our first one, I'm going to add x to both sides first. That'll make it 2y is less than or equal to x plus 2. And then if I divide by 2 on both sides, that's going to become y is less than or equal to 1/2 x plus 1. Sorry, it might be kind of hard to see. That right here says divided by 2. For our second inequality, again, we want to get it into a more easily graphed form. We want a slope-intercept form. So we're going to subtract x from both sides. That's going to leave us with negative 2y is less than or equal to negative x plus 4. Then again, this is divided by. We're going to divide by negative 2. When you divide by a negative, remember that you have to flip this symbol. So it's no longer less than. It would become y is greater than or equal to positive 1/2 x minus 2. So notice how similar these ones are. They both have the 1/2 x. This one, the y-intercept is 1. This one, the y-intercept is negative 2. So these ones are going to be parallel. For our last one, to get it into a slope-intercept form, we just have to subtract x from both sides. And that would leave us with y is greater than or equal to negative x minus 2. So our next step then is to graph each piece individually. And I'm just going to do it by plotting some points, and then I'll use my line function at the top. It might be a little easier for us. So for our first one, we have y is less than or equal to 1/2 x plus 1. So I start at the y-intercept here, right at positive 1. And my slope is 1/2, so I go up 1, right 2, up 1, right 2, up 1, right 2. I can continue in the other direction, and I would go down 1, left 2, down 1, left 2, and so on. So that would be the line that I have there. Again, in this case, because it is a solid line, or because it has the or equals to, we would be using a solid line instead of using a dotted line or dashed line. So I'm going to put my line right there. For our second function, y is greater than or equal to 1/2 x minus 2. Again, we start at the y-intercept, negative 2. We go, because of the slope, up 1 over 2, up 1 over 2. Plot a couple points. Same thing in the other direction. We'd go down 1, left 2, down 1, left 2, down 1, and left 2. See if I can get a red line. Again, this one is going to be a solid colored line because it has the or equal to part. There we go. So that is our first two lines graphed. Now, at this point, I should probably also shade them. This is the highlighter part. If I shade this one in yellow, again, we need to go everywhere less than that line. So it's going to be all of this area. I'm not going to hit everywhere with my shading, just enough to kind of show this is the area that is less than that line. I'll shade this one in this kind of blue color. Again, that's everywhere that's greater than or above this line. So it's going to be all of this stuff. So that's our two regions so far. To finish off our feasible region, we need to graph our last function. Y is greater than or equal to negative x minus 2. So again, I go to the spot negative 2, and I use my slope to find some points. Negative x or negative 1 means I'm going down 1, right 1, down 1, right 1, like so. And I can go in the opposite direction. I can go up 1, left 1, up 1, left 1. Now for this one, again, I'm going to see if I can get a different colored line. Take this kind of green colored line, connect my points. Again, remember it's a solid line because I have the or equals to, and I need everywhere that's greater than that piece. So I want everything that is above this one. I'm going to use this kind of purplish color. Now the spot that we're looking for, our feasible region in this case, is the darkest area. It's the one that all three of them intersect at. So that's going to be all of this region. I'm going to complete it off with just filling it in black. And it continues on off the chart here. We know that it's going to stop right at this corner and right at this corner, but it's going to continue on off our chart as we go. So all we can really do is find the coordinates of those two spots and then find some other kind of test points to check as we look for our function, or as we try to maximize the function. So we can look at our intersections and say, well, right here we have the intersections of two of our lines, and that's at the spot negative 2, 0. Here we have another intersection of some of our lines, and that's at 2, or negative 2, sorry, 0, negative 2. Our x value is 0 here, or right on that line. For the test points then, because this continues to go on off the line, use a spot kind of at the edge of your graph. So we might say, we might use this point right here, 6, 1, or this one up here, 6, 4. Because in both cases, we're kind of moving away from the rest of our vertices there, the other coordinates that we have, moving off, continuing up and towards the right. So the other 2 points that we're going to use, these test points, would be 6, 4 and 6, 1. Now again, I could use, if I wanted to, a spot like this, I could use 7, 2. I could use 7 and 4.5 right here. That's fine because those are kind of off on the edge. But I'm going to use 6, 4 and 6, 1 just because those are a little more even numbers to work with. Now that I have my region or my coordinates, I just plug them back into the function. So again, just like in our last one, I plug in the negative 2 and 0 into my function. So it's not f of xy anymore, it's f of negative 2, 0. Plugging that in, and I would have 2 times negative 2 plus 3 times 0. Well, 2 times negative 2 is 4. 3 times 0 is 0. So negative 4 plus 0 is going to be, oops, this should be a negative 4. It's going to be my value right at that point. Okay. Working with our other spot, we have 0, negative 2. Plug that into our function, 2 times 0 plus 3 times negative 2. 2 times 0 is 0. 3 times negative 2 is negative 6. So as we work that out, 0 plus negative 6 is still negative 6. Plugging in our other one, this one again is a test point. It's not actually really one of our vertices. So this is just kind of a test to check things out. We're going to use f of 6, 4. Let's say 2 times 6 plus 3 times 4. 2 times 6 is 12. 3 times 4 is 12. Add them together and we'd have 24. And our last one, our last test point, 6 and 1. 2 times 6 plus 3 times 1. 2 times 6 is 12, 3 times 1 is 3, add them together and we get 15. So move all these out of our way. Now that we have plugged everything into our function and we've solved things out, we can look and decide, okay, where are we at our maximum, where are we at our highest, and where are we at our minimum, our lowest? Well, our minimum occurs right here, at negative 6. That's the lowest spot that we can get. And our maximum occurs right here at 24. That's the highest spot that we can get. But that 24 was from one of our test points. Okay, that part wasn't an actual boundedness of our region. Okay, that wasn't an edge. That spot continues on forever. So because our maximum actually occurred at one of our test spots or one of our fake points here, we would say that we don't actually have a maximum. Okay, so we would say negative 6 is the smallest, 24 is the biggest from that test point, so negative 6 is the minimum. That's the smallest our function can ever get. But in this case, because our region is going to continue on up and to the right, there is no maximum for our function. Okay, we can plug in bigger and higher x and y values, which is going to make that function become even bigger. So even though we found 24, we could use bigger numbers in our region that would be even bigger than 24. But the smallest number we're ever going to get for that function is going to be negative 6.